Hello everyone, my name is Aryan, and in my previous lecture I have discussed two numerical problems based on Cramer Rao inequality. So today I will discuss one more problem based on CR inequality. So now you can see here, problem is so that x bar in random sampling from fx theta is 1 by theta exponential minus x by theta, okay, where x lies between 0 to infinite and theta lies between 0 to infinite, is an minimum variance bound estimator of theta and has variance theta square by n. Okay, so this is our problem. In question, x bar is an MBV estimator of theta and has the variance theta square by n. Okay, so this is the question part. So come to the solution part. How we can prove that this x bar is minimum variance bound estimator and has the variance theta square by n. So come to the solution part. Now you can see here, let x1 x2 up to xn be a random sample of size n from population with PD of fx theta, and fx theta is exponential form. Okay, this is exponential probability density function. Then likelihood function is defined as, likelihood function is joint density. Now you can see here, L is equal to product fxi theta, and now we can simply put here value of fxi theta. Then what we get here, x is xi. Okay, then simplify it, and likelihood function is equal to 1 upon theta to power n into exponential minus summation of xi upon theta. Okay, is it clear? I have already mentioned how you can simplify likelihood function in my previous lecture when I have discussed two numerical problem. Okay, so after that, taking log both side, we get log of L left hand side, and right hand side is what? Again we have two terms, so log of this into this is log 1 upon theta to power n minus log of exponential is what? 1 upon theta summation of xi. Okay, so now come to the next step. Simplify this equation in form of this equation. Okay, log L is equal to theta to power n, that means you can write it theta to power minus n, and by log property you can write it minus n log theta, and second term is minus 1 upon theta summation of xi. This is equation number 3. Okay, then as I have already mentioned in my previous lecture, how we can find out the minimum variance bound estimator in theta and how we can compare the variance. Okay, so we are following the same procedure here. Now you can see here, taking first derivative of equation number 3 with respect to theta, so del log L by del theta is equal to, derivative of first term is n is constant term and log theta is 1 upon theta. Okay, and for the second term derivative, summation of xi is outside, and 1 upon theta, derivative of 1 upon theta with respect to theta is what? Minus 1 upon theta square. Is it clear? Okay, so now rewrite this equation in form of equation number 4. You can see here, first term is minus n upon theta. Okay, and second term is what? Minus minus plus 1 upon theta square and summation of xi. This is equation number 4. Okay, then again what we are doing here, we are taking the second derivative of this equation. Okay, that means we again differentiating equation number 4 with respect to theta. Okay, after differentiating and getting result, I will explain why we are doing this step. Okay, so now second derivative is del 2 log L by del theta square, del 2 log L by del theta square, and first term is what, minus n upon theta, and differentiating with respect to theta, what will be the result, minus n, and 1 upon theta is minus 1 upon theta square. Is it clear? And plus summation of xi is outside, and derivative of 1 upon theta square with respect to theta becomes minus 2 upon theta cube. Okay, you can simply differentiate it and you can cross check it. Is it clear? Now what is our next step? Next step is just simply rewrite this expression in form of the equation number 5. So del 2 log L by del theta square is equal to n upon theta square minus 2 upon theta cube into summation of xi. This is equation number 5. Okay, and we know that Cramer Rao inequality is variance of t greater than or equal to tau dash theta square upon expected value of del by del theta log L square. Okay, so and what we are doing here, we are taking second derivative of likelihood function. So come to the next step. I will explain you why I am doing this thing here. Okay, so in next step we know that I theta is what, I theta is expected value of del by del theta log L whole square. Is it clear? And we can write this expression in form of this expression, minus expected value of del 2 log L by del theta square. That's why in previous step I did second derivative of likelihood function. And now if I theta is equal to this thing, and we have equation number 5 of for this quantity, so now simply put in place of del 2 by del theta square log L is minus n upon theta square plus 2 upon theta cube and summation of xi. But here expectation is outside, then we are taking expectation inside. That's why we are writing expectation of xi here. This is equation number 6. Is it clear? Okay, so in this problem we have, in given problem, sampling from exponential distribution. Okay, as mentioned in equation number 1. So we know that mean of exponential distribution is what, theta. If exponential distribution form is 1 upon theta e raised to power minus x upon theta, then mean is theta and variance is theta square. This is equation number star. Okay, so now again put the value of xi in equation number 6, then we get I theta is equal to minus n upon theta square plus 2 upon theta cube into summation I going from 1 to n. In place of xi value is theta, and after putting exi value, again simplify this equation and we get next step, minus n upon theta square plus 2 upon theta cube into summation I going from 1 to n becomes n theta. So theta cancel out and resultant reduce in form of this equation, minus n upon theta square plus 2n upon theta square, and final result is n upon theta square. Okay, this is value of I theta. I theta is equal to n upon theta square. And in this problem tau theta is what, theta. Okay, and differentiate tau theta with respect to theta, what will be the result, tau dash theta is equal to 1. Is it clear? Okay, so come to the Cramer Rao inequality structure. Hence CR inequality, Cramer Rao lower bound to the variance of an unbiased estimator of theta is what, tau dash theta square upon I theta. Okay, and we know that tau dash theta is what, 1, and I theta is n upon theta square. So simply we are putting the value of tau dash theta and I theta here, and we get lower bound of variance of unbiased emitter is theta square by n. Okay, this is equation number 7. You can see here, this is variance, lower bound of variance of an unbiased emitter of theta. Okay, so now consider the estimator x bar is equal to 1 upon n summation of xi. In our problem x bar is given, so x bar is equal to 1 upon ni summation of xi, and then we have expected value of x bar is 1 upon n summation I going from 1 to n expected value of xi and we know that expected value of xi is what? Expected value of xi is theta. So just we are putting the value of expectation of xi and we get final resultant of ex bar is equal to theta. So that means x bar is an unbiased estimator of theta.
And variance of x bar is defined as sigma square by n, and in this problem we can write variance of sigma square is variance of x upon n, and for exponential distribution variance of x is theta square upon n. So this is variance of x bar is theta square by n. Okay, and I theta is what? N upon theta square, and lower bound of variance of unbiased emitter is theta square by n. So this value is equal to this value. That means minimum variance bound estimator for theta exists here. Okay, so we can conclude that.
Okay, so thus we see that from equation number 7 means variance of x bar coincide with the Cramer Rao lower bound obtained in equation number 7. Hence, x bar, the sample mean, is minimum variance bound unbiased estimator for theta. This is the conclusion point of solution of first method. And now
Okay, so this is the one way we can find out the solution of given problem, and I have already mentioned one more methods or one more procedure. By using this way we can find out the solution of given problem. So now you can see here.
in next step, I have mentioned here a more convenient way of doing this problem is as follows. We have first derivative of likelihood function is this, and we can write this likelihood function, first derivative of likelihood function, in form of this expression, and now we can simplify it and we get x bar minus theta upon theta square by n, and then we can rewrite this step in form of next step, x bar minus theta upon lambda theta, and which is the form of t minus tau theta upon lambda theta, which I have already mentioned in my previous lecture. Okay, so that means we can conclude that x bar is an minimum variance unbiased estimator of theta, and variance of x bar is equal to lambda theta, and lambda theta is what? Theta square by n. So this is one alternative way we can find out the solution of above mentioned problem. Otherwise, I have already mentioned traditional method, how you can proceed the solution part of any given problem. So it's your choice. You can apply first way to find out the solution, otherwise you have second method. Okay, so thank you so much to everyone for watching this video.